Hey everybody, today we're going to look at a quick video of our Unit 2 Lesson 8 concerning the perpendicular bisector theorem. So this is another theorem that we are adding to what we've learned so far with um, both angles and lines and triangles. And quite simply, there's a couple words here. Again, one word we see perpendicular, right? That means that lines meet at a right angle or all right angles, right? So they cross each other in that way. Um, so that's a property of an intersection. And then we have another property that can happen, which is called bisection or a bisector, which means that it cuts a segment into two congruent, which means equally lengthed pieces. So this is doing both of these things at the same time. So um, if we have a segment here, PQ, so this is a line segment, um, its perpendicular bisector would be a line that cuts it both perpendicularly and cuts the segment into two, right? So that's what that means, right? But it's referring to the line. And so the perpendicular bisector theorem, what it says is that a point, for instance, S or R or T, for example, that these points can only be on a perpendicular bisector if and only if the distance from those points to the end of the original segment is the same length, right? So if I see, for instance, um, these two lengths that come off of point S, the only way that S is on a perpendicular bisector is if the distance from S to these endpoints happens to be the same length. So this applies to triangles because, as you notice, we just kind of made a triangle with those segments. So, um, again, if we can imagine a triangle like down here, triangle NTM, right? We can imagine this triangle there, that um, it has certain properties to it if we know that the number one, that the intersection with the altitude here is at a right angle, and we know that it's a bisector, meaning that those two segments on the side of that um, intersection, that those are equally sized or they're congruent. And that implies that the other lengths are congruent as well. So that's really what we're trying to say here. We're trying to take one piece of information that we know and transfer it using this theorem into more information that we can tell from it. But regardless of where the point is, whether it's really high or really low, the distance from that point to the endpoints of the segment should be equal or will be equal. Sorry, there's no doubt about it. If we have that, if it's on a perpendicular bisector. So this is kind of what that might look like in a figure, okay, like this. If we know that, again, the distance from a, if we know that the distance from a point to the end of a segment is the same as another, okay, then we know that the not only are the distances on either side of that bisector, or again on the side of that intersection, that they're going to be equal, but also that that has to meet in a 90-degree angle. So this is something that applies to what we call isosceles triangles, or in fact, it could be equilateral triangles, but triangles that have at least two equal sides. Okay, so we're going to look at some problems like that. Again, there's some heavy language there, but I think the concept on it is fairly streamlined if you kind of think about this image here and what we're trying to do here, right? If it's very even this way, the symmetry should also be respected in the other way as well. So how does this apply to questions, right? How do we look at some problems this way? So the first, this is an example of a problem here, and again, the this theorem can be used what is called bidirectionally. It works both ways, right? So if we know that this information is true, it implies the other, right? And back and forth, right? Not everything works this way. So if we know this to be true, then we know that if we know that this is a bisector, this has to be true. Also, if we know that this is true, then that has to be a bisector, right? That's kind of the idea. So if we look at this like level 1 type question, we see our triangle HIJ, right? We see this triangle here, and it gives us the length of IJ, which is 46. It gives us the length of KJ, which is 41, and it gives us the length of HK, which is also 41, and it tells us we have this right angle here. So this tells us, again, it's perpendicular and it's a bisector because on either side of that intersection, we have the same length. So this is going to imply that HI is also 46 because the distance from I to J is 46. So the distance from I to H should also be the same, right? So that's the idea that there's that symmetry, that balance here because of the way that the intersection occurs. That same concept we can extend using algebraic expressions. So what we're going to look for here is, again, the information that's given to us, we want to label this information since it's not on our figure, and then that will help us use our spatial awareness to kind of write out any equations or any solutions that we need. So let's start off here and read. So it says if xy equals yz equals 45, okay? So if this is true, so we're going to go ahead and assume that that's true, right? So if xy is 45, so this is 45, and yz is 45, so that's 45. So that is the sort of the tent, the top of the tent coming down. So those lengths are equal, right? So that is implying that these lengths should be equal because of that perpendicular, that right angle there, right? So that's what this is trying to hint at, right? It's telling us that since these two segments are equal, right, then we should expect that down here at the bottom or on the right side. It says WX is 2S, so we'll write 2S. And it says that WV is S plus 14. And it says, what is the value of S? Okay, well, like I said, because we know that these two segments are congruent and equal, and because of this right angle, the perpendicular theorem, bisector theorem applies, which means that S plus 14 and 2S must be the same. So we're going to say S plus 14 is equal to 2S. Again, you could end up with all sorts of different expressions, but from this point, once we have an equation, once we know what to set equal to each other, we can then solve it. The best thing to do in this case would be to subtract S from both sides. This will accomplish eliminating the S on the left side. So we'll only have 14, and we'll combine all of the S's on the right. And thankfully, 2S minus S is just a single S, right? So 14 here will be our answer. Okay. Now, again, the questions can become more complicated based off of what information is given, or if maybe the expressions are listed in a more complex way. But the concept remains the same, and that is if we have a perpendicular bisector, that the segments going from any point on that bisector, any point on this red line, to X and Y should be equal. And likewise, wherever that intersection, that bisection of XY is, we should have the corresponding equal sides on the end.